Okay, hi everyone, this is Lun Lam. I'm delighted to welcome you to the AIRS in the Air Multi-Robot System Lecture Series. Thank you for joining us today. Multiple robot systems are becoming increasingly important as robots are being used in a growing number of fields, such as manufacturing, logistics, inspection, and explorations. This system allows tasks to be accomplished more efficiently and effectively, as multiple robots can work together to accomplish different complex tasks that would be difficult or even impossible for a single robot to achieve alone. Despite the benefits, this technology still faces many challenges in practical application, especially in dynamic environments. To tackle the challenge, many scholars worldwide are making continuous effort into this field and achieving remarkable results. The aim of this lecture series is to promote and sharing the technical advancement in this field, and this event is also supported by the IEEE Robotics and Automation Society, Guangzhou branch, and the Technical Committee of Multi-Robot Systems. And today is the first day of the lecture series. We are privileged to have two experts joining us today to share their insights on this topic. And they are Dr. Martin Saska and Professor Luis Merino. We also have Dr. Junjie Hu to serve as the host of today's talk. He is a research scientist with AIRS, and his research interests includes machine learning and computer vision, and also robotics. All right, without any further delay, I now turn the floor over to you, Dr. Hu.
Okay, thank you, Professor Liao. Today we are honored to have Prof. Martin Saska and Prof. Luis Merino joining us to give talks on multi-robot cooperative systems. Each talk will last for 40 minutes, including a few minutes for the Q&A session. During the Q&A session, you are welcome to ask any questions to the invited speakers. Our first speaker is Prof. Martin Saska, who will discuss his research on tightly cooperating aerial vehicles in real-world environments. Prof. Martin Saska received his master's degree at Czech Technical University in Prague 2005, and his PhD degree at University of Würzburg, Germany 2009. Since 2009, he is a research fellow at Czech Technical University in Prague, where he founded and has a multi-robot systems lab, and co-founded a Center for Robotics and Autonomous Systems with more than 70 researchers cooperating in robotics. He was a visiting scholar at the University of Illinois at Urbana-Champaign, USA in 2008, and at the University of Pennsylvania, USA in 2012, 2014, and 2016, where he worked with Vijay Kumar's group within GRASP Lab. He has published over 200 papers in top-tier conferences and journals with over 5,500 citations. His team has won multiple robotic challenges in MBZIRC 2017 and 2020, and the DARPA SubT competitions. Okay, Professor Martin Saska, please give your speech now.
Hello, everybody. Thank you very much for the nice introduction. Thank you very much for inviting me to this interesting workshop. And I hope my presentation will be interesting for you, and you will learn something what we are doing in Prague and what other researchers are doing in this field. So let me share the screens. I hope you see my slides and you see the video running.
Yes.
Can you confirm, please? Perfect. Thank you. Yeah, so please, in case you would have any question, feel free to interrupt me. Of course, I like more to see if the audience is not sleeping and following me. These remote presentations are kind of like I don't want to say boring, but maybe more boring than to be in present. So unfortunately, I cannot be with you. I would like to be. So hopefully next time I can be in your place and present to you directly. So let me start my presentation. I want to, as the title of my presentation say, I would like to show you briefly what we are doing in Prague in the research of multi-robot systems. I'm heading a group of why it's not moving. Okay, now I'm heading a group of 35 employees in Prague, plus we have a huge group of master and bachelor students. So altogether, we are more than 80 people cooperating on our robots. So we have the ability to cover really all the disciplines required to build a complete system of fully autonomous drones. So all the videos and all the pictures you will see, the drones are flying autonomously without any pilot, without any operator, even without communicating into a ground station. So they are really independent robots using onboard sensors, onboard computational power, or onboard artificial intelligence. And we try to deploy these robots into real world environment. So we don't have even a flying lab where we could fly inside in our lab or even outdoor at our campus. We don't have any place purposely. We want to fly really in the real conditions. So we travel a lot to nature, to cities, to industrial complexes, always where the drones needs to be deployed. Here you can see also a kind of wall of fame. We are proud of successful participating in multiple robotic competitions. I will briefly tell you about it a bit later. So let me start with the main story, which is the swarming. This is the main discipline we are involved in. Yes, sorry for the short interruption. So swarming where we are focused in is mainly flying in a GNSS denied environment. So flying without GPS. Even we intend to fly without any direct communication between the robots. So the robots are really independent agents, but they are observing their neighborhood. They are observing the other robots in their proximity using onboard sensors. As you can see in this picture, the robots are flying autonomously in a forest, avoiding the trees and communicating to each other just by observation. So each of the robots is equipped with a system UV that I will show you a bit later. And they are using this information to build the formation, the swarm, and doing a job without communication. Our systems are strictly decentralized. Obviously, you cannot have centralized system if you don't have communication. We fly in an unknown environment. Usually the real world environment is unknown for robots. Of course, we can use the maps as well. So we do SLAM, we do mapping, we do navigation. So all these disciplines are crucial for deploying, reliable deploying of robots in real conditions. We want to have our groups of robots scalable. Therefore, we try to apply bio-inspired methods. We try to be inspired by birds and fish school and a flock of birds and insects to use these principles to be able to fly similar as these guys are doing. I don't know why it's not so well working today. We are proud of our system. We have designed for controlling of multiple robots. We call it AIRS UAV system. It has now more than 1,000 active users. You can find details in this publication. Part of the systems is, or the main part is the control part, where we have multiple controllers you can choose from. We are using SO3 controller or MPC, model predictive control. We have embedded there multiple trackers for tracking of trajectories or desired references the drones are using. We have there also possibility of fusing multiple sensors. So as I have mentioned, our robots are using onboard sensors mainly. So they can be equipped with cameras, 3D, 2D lidars, radars, a lot of different sensors, 3D cameras. And often we try to combine, fuse multiple of these sensors together to get a reliable output. Because the state estimation for the robots is, of course, crucial. The robot needs to know their state to be able to control them, and therefore our researchers are also focused in this particular area. Yes, as I have mentioned, we have multiple controllers there, the MPC and the others. But I would like to focus on a unique sensor, smart sensors we have developed here in Prague, which is intended for large swarm of robots in real world conditions. We are using UV LEDs mounted on robots. We have selected the UV part of the spectrum because using RGB cameras are sensitive to illumination. We have found, and you can see the example on the picture here on the right, that in the RGB spectrum, it's really difficult to find the drones around, even if you are using the advanced AI methods, neural networks, and this kind of stuff. It's difficult to detect that there is a drone in front of this car. And this is relatively nice illumination. You may have really darkness. You are like here. You may have really difficult conditions for the image processing. But with UV, as you can see here in the spectrum of solar radiation, the UV part of the spectrum is relatively rare in the sunlight. Therefore, the sun is like not providing this part of the radiation, and it's not reflected from the objects. That's why in this picture, you can see really only these two bright dots, which is the drone equipped with this UV DAR system. So detecting these bright dots, we can simply detect the drones around, track them, and even communicate through blinking of these UV markers. So we can have a simple indirect communication that each drone can blink, for example, their status. It can inform the other robots that the drone is landing and so on. Another interesting research we are conducting right now is trying to use the swarm intelligence for solving situations where one of the robots or few robots from the team is kind of blind at all. So you may imagine flying above, for example, a desert where you have sand everywhere, and you want to be relying on camera. Obviously, there are no obstacles in the desert, so you cannot use 3D lidars to localize the drone. So you may use cameras on board. But of course, above the desert, there are places where the sand is consistent and you can't see any stones, anything, any object. And in this particular situation, your drone would be completely lost, and you would even track, lost the state estimation of the velocity, which is crucial for the drone, and the drone would collide immediately. But we have found that using multiple robots in the team and helping the other robots, which are maybe better localized, that these robots are helping the poor localized guy, as it's possible to see here, this robot can improve its own localization performance, and all the guys together can fly. So here you can see an example of 7, if I'm not mistaken, 7 drones flying together. It was 6. One drone was for as a target. And these 6 drones are flying 40 kilometers per hour without GPS. So they are not using GPS. They are not using communications. They are just observing each other. And we have even found some locations above this grass that the particular drones are completely losing the track. They are not possible to be stabilized because the green under them is like persistent and without enough visual features. But even in these regions, the swarm is stable, flying really fast. And also, you can imagine that such a swarm is difficult to hack. For example, you can't spoof GPS because we are not using GPS. You cannot spoof the communication. We are not using communication. But it is a really interesting research to really try to exploit the fact that we are flying in the swarm and help the individuals. Now, let me briefly tell you some lessons learned we get during our deployment in the DARPA subterranean challenge. It was really great challenge because it was really pushing the research on the edge. We were the aim of this competition was to find some victims in underground environment. We, as human or as operators of the drones or ground robots, were not allowed to enter the environment at all. So we had to send our team of robots, just go guys, go there and explore the environment. We even didn't know what type of environment is in front of us. So they didn't allow us anything. So it was really unknown environment. So usually unknown environment for you means that you know that you will be flying in a forest. So you can prepare your drone or your system for flying in the forest beforehand, right? You can like train your neural network for the trees around and so on. But here we couldn't train anything. We didn't know if it will be a cave or a tunnel or how the environment will look like. So it was really challenging task. We managed to win this competition among self-funded teams. We were third in together. The same happened also in the second part of the DARPA challenge in urban circuit. And it was again the same example. We were targeted to explore the environment of nuclear power plant. So our robots were sent to the power plant without a priori knowledge. They were flying there and we had to design the system in a way that they are able to explore really tiny corridor or almost touching the walls by their probes, and as well as flying in the huge, as you can see here, huge areas of the power plant. So our system tried to adapt by itself just by observing the environment. So this is a completely new view to the robotic, where the drones are observing the environment and changing their behavior based on the environment properties to be able to be fast and efficient. In the final of the DARPA SubT, we were second at the end in the virtual track, and this was really a really great lessons we learned there. Was the DARPA organizers, they built a special stage for us where the robots were deployed. They built an artificial train station, as you can see here. So everything was built from scratch by them. So they built a train station. They built a coal mine, and they built an artificial cave system. So we sent the drones there, and the drone flew into a metro station. Then it continued to a mine. Then there was a cave. So it was really, really heterogeneous system for being deployed in heterogeneous conditions. So it was really something which pushed a lot the robotics, and we could see even in observing the other teams. Then the key issue was to design a really reliable system. So this is our main research intention right now, to build the drones which are really reliable, which are kind of never crashing. Of course, this is a difficult task, but we try to go forward. So as I said, the DARPA SubT challenge was really pushing the state of the art of robotics. So we managed to have a lot of publications in the best journals in our field out of the competition, which is great. And we managed to have also a lot of industrial outcomes. We are now applying the system from DARPA for monitoring of historical objects, as you can see here in these examples. And in this particular scenario, it is extremely important to again have a high reliability, because you can imagine that destroying such a valuable historical objects in the churches or cathedrals we have in the Czech Republic and around. We are flying also in Germany and Poland. It's of course no way. So we have to have really an extremely reliable system that we have built. The nice thing is that we have even found some applications where multiple robots being deployed simultaneously is necessary. So here in these examples, you can see that the object is with insufficient illumination. The lightening there is not sufficient. So we have to deploy a team of multiple robots where one of the robots is carrying camera, flying completely autonomously in the church. And another drone is forming a formation with the main guy, here as you can see here, carrying a light. The advantage of such an approach is that you can point the light from side, so you don't have to put the light on the same drone as the camera, which makes much better quality of pictures. Of course, we are using also 3D models scanned by the drone. These 3D models are used for the end users to plan the mission. Of course, here in this particular application, the drones are not flying randomly in the environment as it was done in the DARPA SubT, but they have to follow a predefined set of locations to visit and to make a picture there or to scan the object there. So this was the outcome of the DARPA SubT. Now let me briefly go through the MBZRSC competition, where we have also successfully participated. In the first round of the competition in 2017, we won one of the challenges. So we were first place in one of the challenges, and we were second in the second challenge. Here in 2020, we were first in one of the challenges, we were second in another challenge, and we won the competition entirely. So we were the best out of the 250 teams from the world. Even a lot of teams from China participated. One of the teams from Beijing was really good. They won one of the competitions. We were the second behind them. So congratulate. I have to congratulate to the guys if they are here as well. The challenges were to capture and neutralize intruder UAV and and then to build a wall from bricks and also to extinguish a fire. Again, all these challenges were pushing like the limits of the robotics, therefore we could publish it a lot. So if you are interested in details, feel free to see these publications or let me know and I will send you PDF. Yes, so as I mentioned, it was really a lot of publications we achieved from this competition. Here are some pictures from the competition. So as I said, one of the first challenges was capturing some flying objects and also static objects, so the balloons and the flying objects here. So the task was to capture this really tiny ball which is carried by the drone. The second challenge was to build a wall from bricks, fully autonomously. So the drones were equipped with a gripper, magnetic gripper, to grasp the bricks and place them to the locations which was given. So you can see the wall here where the bricks were placed. As I said, everything was autonomous. We couldn't touch the keyboard or controller the drones were flying really without any help of the humans. And the last challenge was firefighting of high buildings. I believe in China you have these problems as well as they have in Emirates, in Abu Dhabi, where the competition took place. So it's obvious that we have to fight with fires in these tall buildings. So the competition motivated several companies. They contacted us, and we are now building firefighting drones, which are not the toys as you could see before for the competition, but they are carrying real systems for firefighting. Here you can see one example of such a drone. This is a small model of fully autonomous drone, which is used for firefighting. So it's a small-scale model. The drone is carrying only one capsule of the system for firefighting. But we could demonstrate with the firefighting brigade that we are able to autonomously reach the location, detect the window with the fire, put the device for firefighting inside fully autonomously. So the drone is shooting these capsules with a special liquid into the fire autonomously, just by observing the heat source of the fire. So the drone is equipped with a thermal camera and shooting it to the target. Now we are building a full-scale drone, which is capable of carrying 25 kg of the firefighting liquid, which is already sufficient amount for firefighting fighting with fire in a regular size flat. So with this drone, you should be able to stop the fire in a regular size flat and save the people. Here you can see some initial testing of shooting these firefighting grenades by the big drone. Another example of deployment of our technology into the industry, which was in fact motivated by the competition, is a drone which is used for capturing non-authorized drones. So this drone is intended to protect airports or some important buildings like nuclear power plant, for example, or even to protect privacy of rich people or celebrities. So you can buy even this drone if you want. And the drone is equipped with a system for capturing of other drones, which were in fact designed initially in the MBZRSC competition. So here you can see a deployment of the system for protecting of an airport. Here it's an intruder drone. So there is this DJI Mavic drone flying into the area. The drone is detected by an external system, which is consisting of 3D LiDARs and antennas to detect the communication between the pilot and the drone. Once the alert is triggered, our drone hunter Eagle 1 is launching from the heliport, approaching the target and catching the target safely. So in comparison to the other systems, which are shooting the drones down or using birds or whatever, our system is really safe to the environment, like to the other people around or to the other objects, because the drone is catched and carried by the Eagle 1 to a safe place. So this was the Eagle 1 project. This is another project which we are working on. It's an inspection of power lines. I will rather skip this this project bit because I want to show you more interesting one at the end. But we have achieved already a lot of interesting results. We are even deploying a system which is able to cooperate with humans. So this drone is tracking the human, even observing gestures of the human, to be able to cooperate. So in my vision, the cooperation of drones and people is in a near future because the system is already there. We have ChatGPT, we can already communicate with a robot easily by voice. by sending messages. So, or even using some gestures as we are working on. So this is, in my opinion, the future of robotics, that the drones, not only humanoids as it is now, but even the drones will closely cooperate with robots and sharing their environment. Another project I would like to mention is a project on localization of sources of ionizing radiation. So you can imagine that you have a source of radiation which is stolen or used for a terrorist attack, and it needs to be found as soon as possible. We have designed a system using multiple robots to detect and track these dangerous objects by using really small Compton camera detectors which are carried on board. So even with this extremely small but powerful detector, you can localize a large or a small object of radiation. Another project we are working on is a project focused on marine operations. So we are designing a system for boats, cooperating boats and drones. We are able to land in really difficult conditions of the waves. So here are some testing we did in our lakes, but we did also a lot of testing in the real sea under real wave conditions. So we showed that we are able to control the boat, of course, this is easy. We are able to cooperate to control both the drone and the boat together as a pair. We are able to estimate the position of the boat for landing. Of course, we can land also on the water, as will be shown here, but this is easy. But landing on the boat, if it's affected by the waves, if it's in really difficult conditions like this rain you can see here, this is the challenging task. Yeah, I wanted to show you at the end the successful landing, but I believe you trust me. So at the end, you can see how we can land. Yes, I want to also show you that if you would like to use the system we are designing, you can, everything we are using is open source. You can follow us on GitHub and use all our codes, but you can also use our drones if you like them. You can just simply follow this link, this dronebuilder.flyforfuture.com, and you can build your drone in this kind of e-shop. Then we will help you with assembling the drone and prepare the drone for you ready to fly. So it is kind of easy for you to get ready to fly platform with software. Another announcement I would like to do is on our summer school. We are organizing every year in Prague. It is focused on multi-robot systems. We have usually 8 excellent professors from the best universities worldwide. And we have also a lot of students from excellent universities. So I hope you can still join us in July this year. If not, the next year there will be a repetition for sure. Last time we got 240 participation. And the interesting part of the summer school is that we are flying, like all the students are flying with real drones at the end of the summer school and doing some experiments with the robots. So the final day of the summer school is kind of a competition for the students where they get our drones, and they have to solve some tasks. So this year, the task will be motivated by inspection of solar power plants, the panels of the power plants. You know, it's useful to do it by drones, but do it by multiple drones cooperatively. So during the summer school, we have a lot of seminars, as you can see here. We really push cooperation between the robots. We have the lectures, and we have also the practicals. So during the summer school, students are getting the knowledge how to fly a real drone, not only a real drone, but a swarm or a formation of real drones that are cooperating. And these are the pictures from one of the final competitions where the drones were targeted to detect these flags. So we placed 20 flags into the environment, and the team of drones, 2 cooperating drones, which were kind of programmed by students. So they were able to detect even 3 drones, as you can see here. They were able to detect the flags. It was very successful by the students. Okay, so this was everything from my side. I hope I'm on time. We have perfectly almost 40 minutes, so we have still plenty of time for questions.
Okay, thank you, Professor Saska. Very impressive. There are also many Chinese audience watch this talk from different platforms, and they get a question from Xie Guo. He asked, in your applications, is the communication requirement high for multi-robot system, especially in underground environment? Will there be robot disconnection situation?
Yes, exactly. This is a very good question. In fact, we know that it's really challenging to communicate between the robots, and it's extremely challenging to communicate within the large team of robots. That you have the scaling problem. So even if you are able to communicate with 20, 30 robots, you are not sure that your communication infrastructure will allow you to deploy hundreds of robots. And going to 1,000, it's impossible that each robot would communicate with each other. And as was mentioned here, if you are in the underground or underwater or in really hard conditions, the communications is usually not allowed at all. And of course, you have also defense applications where you don't have to communicate purposely. But even in that subterranean challenge, we figured out that the drones can communicate only if they have direct visibility. If one of the drone was behind the corner of the corridor, it couldn't communicate. They lost the communication channel, of course. There are the stones around. Therefore, we are trying to design our systems which are reliable enough even without communication. So as I have mentioned, most of our teams of robots are not communicating at all. Of course, if we have the communication, we allow the robots to communicate. So this is, in my opinion, the very important thing, not to rely too much on any source of information. So if your system will be designed and requiring the communication not being interrupted for the entire mission, most probably you will lose your drones. Because this always happens, that there is a problem with communication. Even imagine that you are using your car going somewhere and sometime and calling during the drive. Sometimes may happen that you are in shadow of the communication infrastructure. If you are in a huge forest, if you are in a canyon somewhere, always there are troubles with communication. And the robots we purposely want to deploy in an environment which is difficult for communication. Like, for example, the buildings, right, inside of the building. So not only communication, but also other sensors, like GPS. You can't rely on GPS. Of course, it is good to use communication. It is good to use GPS if it is allowed. But if not, the system must rely on other sensors. Hopefully I answered the question. Thank you.
Okay, thank you. Okay, there is another question. The audience asked, how do you make sure the solution is optimal? If drones are fully autonomous, multiple drones could crowd into the same place.
Excuse me, can you repeat that the drones can collide, or what was the end?
Yeah, like the audience asked, how do you make sure your solution is optimal? If drones are fully autonomous, multiple drones could crowd into the same place.
Okay.
Yeah.
Yeah, thank you for the good question. I didn't mention that our system for a relative localization of robots, so this is this UVDAR system, is able not only to detect that the drones are around, but we are even able to detect how far the other drones are. So as I have mentioned, the drones are equipped with multiple UV LEDs. So we are able to detect always at least 2 LEDs on the drone. And by knowing the distance between the LEDs, we can measure or estimate the distance of the drone. So you can imagine that if you have in a picture some object of known size and you have the model of the camera, you can estimate size of this picture in the image. So we are using this information for relative collision avoidance. So since the drones know where are the neighbors, and also they can detect their motion, so they can even estimate where they will be in future. And this is extremely important for this collision avoidance or even avoiding for example, a narrow passage problem. So imagine that you are leaving a football stadium after the match. And you have to, all these 50,000 people, they want to go through a narrow door out of the stadium, right? So they have to pass this narrow passage. And what you do, you observe your neighbors. And of course, you don't want to have a panic there. So you kind of coordinate yourself with the others to safely pass through the doors, because you are estimating the behavior of the other people around you. And we do the same. We observe the drones which are in the proximity, and also we try to estimate their further motion to be able to coordinate them and to let them pass, for example, these narrow corridors safely and not colliding. And of course, the other obstacles, they have to be detected as well. So we are using 3D LiDARs, 3D cameras, or even a combination of multiple sensors to be able to detect the obstacles in the environment.
Okay. There is another question that asks, are you using PX4 as an online system, or you build your own multi-robot system?
Yes, we are using PX4. So far, we are really relying on PixHawk. But I don't know if you have experience with this system, but for example, like recently, they released a new PixHawk with PX4 system on board. And this sensor is absolutely unreliable. So we found out that by the new revision, the system is not reliable. We are waiting for updates, which is really annoying. So currently we are designing our own flight controller with our own system, and the MRS system which I have presented, and you can find online, open source. So this system can rely on any flight controller. So we are not strictly depending on the PX4 or PixHawk, but in most of our systems we are using it so far. But we don't want in future, to say true.
Okay, Prof. Saska, thank you very much. Due to the time limit, we will finish the first talk. Actually, I also have several questions. Maybe I will send you the email later. Okay.
Yes, okay, please. If you have further questions, please send it to me, or students can contact me directly. Here you can see my email in the slide. And of course, it's possible to share the slides with the students as well. So if you are interested, let me know, and I will send you the slides. And yeah, thank you all for attending my lecture, and thank you for the great questions.
Thank you very much. We would like to invite you in the future, maybe. Thank you very much.
Yeah, definitely. I would be happy to visit you, and all you are welcome to Prague. Let me know, or come to our summer school. Thank you.
Okay. Thank you very much. We will go to the second talk. The next invited speaker is Prof. Luis Merino with a topic on active perception for exploration with multiple robots using information theory. Dr. Luis Merino is an associate professor at the School of Engineering of the Universidad Pablo Olavide, UPO, Seville, Spain, where he leads the Service Robotics Lab. Prof. Merino led the creation of systems engineering and the automation division of UPO School of Computer Science, where he has been the vice dean for 5 years. He holds a PhD degree on robotics from the University of Seville. His thesis was awarded with the ABB Award to the best doctoral dissertation on robotics 2007 in Spain, given by the Spanish Committee of Automation. His main research lines deal with cooperative robotic systems, including multi-robot systems and the cooperation between robots and persons. Prof. Merino is leading or has led UPO's team as PI in more than 15 international and national projects. He serves as associate editor of the Image and Vision Computing, IEEE Robotics and Automation Legends, ICRA and AIRS. Okay, Professor Merino, please give your talk from now.
Well, thank you very much for the invitation to the seminars. I'm really glad to be here. It's always very complicated to give a talk after Professor Saska. It's really impressive, the research there, and I really recommend any people here to attend to the multi-robot school, summer school, because it's really, really one of the best, if not the best, that you can have. So really, really recommend it. Okay.
Thank you.
Yeah. So, okay. So, as I said, my talk today would be more about exploration using multiple robots. As you mentioned, my name is Luis, and I'm located here in Seville in the southwest of Spain. If you want to know a little bit more about our group, you have there some directions and email. But before going to the main topic of the talk, let me just put some context of the different contributions I've been myself and my team doing to the multi-robot perception topic in the last, I have to say now that nearly 20 years. We are getting old. So since my PhD, and just to put in context a little bit the research I will be presenting later, okay? So actually, one of the first things I did here on this topic was, well, more than 15 years ago in the COMES project. And there, we use a fleet of aerial robots for the problem of forest fire detection and monitoring. So we wanted to combine the information from different vehicles, aerial robots, in order to estimate the fire front and see what was the situation during forest fires. At that time, you see, there were no quadcopters. We were using, they were even not called drones. We were using RC helicopters and blimps. But we were able to demonstrate that the vehicles they have operational autonomy. They could move to waypoints autonomously, fully autonomously, in this case using GPS. But the idea was that combining the information from all the vehicles, we wanted to estimate this situation of the fires. And actually, while one important point here, and I wanted to relate to the former talk, while there were some distributed operation here, so there was some processing taking place on board of the vehicles at that time, and we're talking many years ago, basically all the processing and all the combination data fusion happened in a centralized way. And as Martin just said before, this is very problematic because first it's not scalable, but then the centralization is a kind of critical point that it fails, then everything fails and nothing can happen. So in the following project I was participating and now directing my first PhD student, Jesus, we first moved to having decentralized perception. And I wanted to just use this slide just to present what I mean by decentralized. Basically, a decentralized system is one system that it relies only on local perception and, if so, local communication with the neighbors. And you don't need or you don't rely in any broadcasting facility. So you only have to, you can only communicate locally with your neighbors or with with yourself, so to say, and also only local communications. And actually in this project, the application scenario was also a kind of emergency scenario in which we had to fight fires in a kind of building. And there was a fleet of vehicles there. And among other tasks, they had to estimate the position of the firemen using the cameras and also other sensors that were deployed there. What we did there is that we developed a perception system that was decentralized in the sense that using only local communications and only this local perception was able to estimate a very similar final result, final tracking as compared to a centralized system. Actually, in the linear case, we demonstrated that it was exactly the same estimation, and in the nonlinear case was an approximation, but using also this, as I said, decentralized. Decentralized systems are very convenient because they scale much better and they are much robust to these connections, because still the robots can work together even if they don't have connection with the rest of the fleet. So after that project and having worked on the centralized perception, we then moved to the next step because still decisions were taken centrally. So we wanted to also decentralize the decision making, and in particular also to be able to reason about the uncertainties that are present in any real problem, because either you have problems with the sensors or you have occlusions, and et cetera, et cetera. And then this is the EasySense mobile project. We moved to that direction. So basically in this project, we wanted to tackle applications like, I hope I can explain here well. We wanted to have a kind of UAVs monitoring a kind of mock-up city in which we have these cars. And we wanted to these UAVs to detect the cars. And when they were detected in a kind of neighborhood, we wanted to track them. The thing is that we wanted to do this in a decentralized way, and more importantly, also to deal with uncertainties. For instance, if you have bridges like this, or tunnels, sorry, like this, you could have cars going there whenever the cars were in the tunnel. You will have occlusion, so you will not be able to see that. But we want to reason about, because we can have models, and we wanted to reason about the uncertainties there. So for that, what we did was to use partially observable Markov decision processes, or PONDPs, so that we can take decisions under uncertainties. And actually, in the system, each UAV was working in its own, using the information coming from the others, using the decentralized data fusion system I mentioned just before. And they were able to reason about the uncertainties in order, for instance, to, whenever a car went into this tunnel, the UAVs could decide, okay, I know that something will happen here. I don't know if the car will go to the other part or will go backwards. This was a kind of adversarial scenario. And the UAV just collaborated at the high level in a decentralized way in order to take the good decisions, okay? And well, in these papers, you can see a little bit more the details, but the main idea here is that also the decisions were taken locally. Regardless of this, we were able to achieve similar performance to centralized systems with access to all the information. Finally, and in this kind of historical view, a little bit of contributions, we also participated in the MBCIRC challenge, in this case in a joint team with the Polytechnical University of Madrid and the Poznan Institute of Technology in Poland. I think Martin already presented the challenge, so I will not tell it again. But we also participated in this challenge 3 about firefighting in buildings, and we ended up 7th in the challenge 3 proper. But then we participated again with each challenge and the others, and so Professor Saska's team ended 1st, and we ended 3rd in this grand final, and you can see the results there. But just in this scenario, as I mentioned before, a team of robots had to collaborate in order to put out the fires in a mock-up of a building they built there, and they simulated fires using different components like with this red silk, but also with infrared emitters, and also with real fires with gas, as you can see here. And we used a team of robots like this ground robot and then other aerial vehicles, and they had to collaborate in order to extinguish the fires, as mentioned before, either with water or also with these fire blankets. for this, we use a team of robots. And again, we use a completely, again, as Professor Saska said, we follow the same approach. We had a really decentralized system. Each robot was working in its own, and they only collaborated in this case very loosely because we had task allocation. So each robot was tasked with a different task, sorry for the redundancy, like extinguish a fire in a facade, or extinguish the fire inside, or extinguish the fire outside. So there was not that much collaboration. But I wanted to use this example to introduce now the main topic of the rest of the talk, which is about the exploration. So one of the things we needed to do is to explore. In this case, for instance, the drone was exploring the facade of the building, looking for a fire. And then at some point it finds the fire, it reduces the uncertainty on the position of the fire. And whenever the uncertainty was below a certain level, we switch to the attack mode, and then we just control visually the drone. Hopefully you are seeing what you see on the right-hand side is the infrared image from the drone. And then we use some visual control to control the drone. And hopefully you can see here how the drone was just putting water into the fire. So one of the topics, and as I said, will be the remainder of the talk, I will be talking about this exploration. So when we need to, in an unknown environment, we need to map or to determine the location of something, and we wanted to see how we can do this in a clever way. So as I said, this will be the main topic of the rest of the talk, and this was not considered in the former works I just presented. And this work has been carried in collaboration with, we have a collaboration now for several years with the German Aerospace Center, the DLR, actually with the Dr. Dimitri Shutin's group. And the work I'm going to present now is also the work from my collaborators, my PhD students, Alberto and Valentina. So let me just introduce this exploration problem, and I will present briefly some solutions we have developed for that. So imagine that we have one of the scenarios like the ones I presented just before, or this one, which is a real photo of a gas power plant that exploded. And in this kind of situation, we may be interested in exploring one part of it, for instance, to map the concentration of gas or we will be talking here about the exploration of spatially distributed processes like the gas concentration or radiation concentration, or you can think about radio frequency signal power or anything like this. And I hope that from the former examples, it's clear that these kind of applications, robots are very interesting tool because typically, well, they may access places that cannot be accessed by humans, and also they can be very fast, in particular in the case of drones. And the idea is that we would like to plan clever paths in order to map all these spatial process as efficient as possible. And these kind of problems render very adequately for the case of multi-robot systems, because if we have several robots, then we can do this even more efficiently because they can share the task and then divide it, ideally the time by the number of robots in the time needed in order to explore the whole thing. And actually, again, what we want to do this is in an efficient way and possibly in a decentralized way, so this can scale and is robust to disconnections and lack of communication. In particular, the objective here is not only that, but also, as I said, to reduce the uncertainties as fast as possible. So for the remainder of the talk, what I would do is just to present the main components of this kind of active exploration systems in the single robot case very briefly, and then give some ideas of our system and how we extended this for the multi-robot case. Assumptions for the algorithms I will be presenting here are the following. First, we will consider situations in which either we have some kind of external localization system, like we have access to GPS, or we have a localization system, but in which the uncertainty can be neglected in this case. So in some cases, this is a too strong an assumption, but we will be focusing more on the exploration part here. And as well, we'll assume that we know the obstacles in advance. And we want to explore a spatially distributed process, but we will assume that this process is time invariant. I've been talking about efficiency, so now I wanted just to mention here what I mean by that. So whenever we want to reconstruct this spatially distributed process, What we mean by efficiency is basically the speed with which we are able to reduce the error with respect to a ground truth if we have access to this ground truth. So in this situation, for instance, here, we have the, let me just use just a moment this, yeah. So if we have the square error here, so these two, if we compare these to the algorithm, we would consider that B is more efficient than A because basically B reduces the error faster than A. And this would be our criteria for efficiency. So let me then present for the single robot case the typical, the typical algorithm for model-based information-driven exploration. So imagine we have a drone like here, and we want to map, in this case, some spatially distributed process, for instance, a height map. So we want to map the height profile of an scenario. So the typical loop for this information-driven exploration would be the following. So we take measures with the sensors, for instance, the sonar or LiDAR or whatever. Then with these measures, we update any model we use of our process. With the model, hopefully, we will be able to compute some information metric that allows us to estimate the amount of information we will gain by measuring in new positions, and then we will move to the highest informative position. Okay, so this is the typical loop, and then we repeat here. Regarding the model, we have been using for these kind of applications, we are using Gaussian processes. I guess that most of you are familiar with this, but just for the sake of completeness, I will very briefly summarize what a Gaussian process is. So a Gaussian process is just a collection, it's a non-parametric model. It's a collection of random variables, and the idea is that any subset of random variables of the Gaussian process has a joint multivariate Gaussian distribution. And a Gaussian process is just fully specified by two functions. The min function, which basically encodes any prior information you have about the values of the process. And typically this is set to 0 in our setup, but if you have any previous information, for instance, you have a previous map, an old map or something, you could use it like here. And the second important element here is the covariance function, that for any two poses, it gives you an idea of how correlated will be the measurements taken in these two positions. And typically this is you can use different functions for that with different hyperparameters, but for instance, here you can see the typical covariance function, which is the square exponential kernel, which basically will tell you that any 2 points that are separated more than this typical scale length will have measures that are uncorrelated. And the correlations will decrease smoothly with the distance between the points. But you can use many other kernels depending on the type of process you are measuring. The interesting thing about Gaussian processes is that given some measurements you already taken, and we will represent them by this X and Z, so you have, for instance, with your robot, you have explored a little bit of the process already, you can make predictions on the values of the process in places you have not visited yet that will be represented by this X star. And more importantly, you can not only predict the value, but you can predict the uncertainty you have. Okay, so you can predict the covariances over the places you have not visited yet. And then, before that, the only thing you need to is a non-parametric model, the Gaussian process, but you have to learn the hyperparameters of the kernels, and this can be done from data. So, but if we have this model, we can use this predicted uncertainty to determine the informativeness of new points to visit. And typically what is done by many people is to use here the entropy given by the Gaussian process. In the case of the Gaussian process, as we are talking about the Gaussian distributions, the entropy is directly related to the determinant of the covariance matrix if we have several multivariate distribution or the variance directly. So the idea with this type of methods is that if you go and measure in a place where you have a big entropy, you will have a big reduction of uncertainty, so a big information gain. So this initial algorithm, which is greedy, typically will do that. So it will go just directly in each step to the point from the action space that has the highest entropy. For instance, we applied this in some experiments for mapping the magnetic field of a room. So we have this omnidirectional robot here with this sensor. This is a magnetic field sensor here. And you see something, this could be the kind of trajectories that you will get In this case, at each time step, the robot, the action space is just the 8 neighbors. We discretize the action space, so the robot can go ahead, backwards, to the sides, or also to the diagonals. And it will select from all these 8 actions the one that go to a point with the maximum entropy among the 8 points. And you will see how the robot is able to explore and map this magnetic field. If you use this kind of algorithm, then you see that they are much more efficient than other algorithms, like just systematic exploration using a meander algorithm, or for instance, random exploration, and so on. And these kind of algorithms can be very quickly expanded to the multi-robot case. One way to expand to the multi-robot case would be just to, well, deploy the same algorithm in each robot. So each robot could do the same. So you have several robots, so each robot will apply the same loop. So we measure, we update our Gaussian process, we compute the information metric for any of the actions from our action space, and then we carry out the action that maximize this information metric. And we do it for each robot. Of course, if we do it separately, then the robot will be just repeating the same job. But if we allow some communication between them so that they can share measurements and they can compute the same Gaussian process, then there will be an implicit coordination because they are reasoning about the same Gaussian process. And if we share also the positions of the robot, then they can coordinate in order to avoid collisions and so on and so forth. And actually, if you see in this video, we applied this very simple algorithm to the problem of mapping this height map here. So these 2 drones are basically each one of them applying the same basic algorithm. Just we again discretize the action space, and they are moving towards the next action that maximize this entropy on the Gaussian process that represent the height here. And they, after each measurement, they share the measurements and they share their positions in order to reconstruct the same Gaussian process. And also they avoid the actions that leave them to be very close to the other to avoid the collisions, as I said before. Again, if you compare this strategy against other kind of strategies or just a single robot case, by using several robots, you will end up with, again, efficiency gains here. Also, our system in this case is able to learn in online the hyperparameters of the Gaussian process. If you compare here, this kind of bluish line is the system learning on the fly the hyperparameters, while if you knew the hyperparameters in advance, you of course could do much better, but this is very unrealistic because the typical thing is that you don't know the exact hyperparameters of the Gaussian process. And then in the below graph, you can see how the 2 robots, they learn very similar values for the hyperparameters in this case of the kernel we are using in the Gaussian process. But the problem with this, well, final slide is just, here is a comparison of the trajectories of the robot. On the right-hand side, if you have to learn the hyperparameters of the Gaussian process, on the left-hand side, if you know in advance the ground truth hyperparameters. Of course, in the right-hand side, you first has to move a little bit around without any knowledge about the process. So this is why you see this kind of straight lines at the beginning, because the hyperparameters are not known. So you don't know exactly how well the correlations are. But at some point, you learn them, and then you begin to move in a similar kind of exploratory way, as you can see on the left-hand side. But the problem with this kind of approaches are related to the problems we just mentioned before. So the first thing is the kind of approaches are very simple to implement, but they are myopic. They are greedy. So basically, you select directly the action that maximize the next entropy, but you don't reason about the effects of your actions towards the future. Also, we were considering just autonomic robots, but we wanted to have approaches that can be applied to other kind of kinematics. But the main problem here is this one we mentioned before. So we need communications, and we need to share all the measurements so that all the robots can rebuild the same Gaussian process. And this is very negative because this means that the system, basically at the end of the day, it works like a centralized system. So it requires communication between any pair of robots. Furthermore, the approaches presented there cannot deal with complex constraints that I will just mention in a minute. So what we developed here in this project, in this collaboration with DLR, is to a multi-robot exploration algorithm that is non-myopic, so it plans. It can be applied to different types of robots, taking into account their kinematics, like, for instance, fixed-wing aircraft or car-like robots that perform a distributed decision-making and that can handle inter-robot constraints. And what kind of constraints? Of course, avoiding collision between the robots, but also sometimes in some applications, we want to maintain a network communicating all the robots. I'm not meaning a mesh network. We don't want to maintain a all-to-all communication, but we want to create a network so that even using multi-hop, any robot can communicate to another. And this could be needed in some application scenarios. So these are the constraints we wanted to consider in this approach. So in order to achieve or to tackle all these challenges, I will show how we expanded the former simple exploration algorithm and the main components there. So on one hand, we want to now not to take the greedy next action. We want to pass informative plans. And the framework we use to plan paths is RRTs, which I guess are very well known, but I will very briefly just indicate some properties of it. And then in order to coordinate the actions of the fleet and take into account the constraints, we use a distributed constraint optimization method. Still, we use Gaussian processes as our model of the environment, but for the information metric, we will be switching from entropy to mutual information for reasons that I will explain shortly. So as I said, the first component is very well known, RRTs for planning paths. Basically, as I said, this is very well known by everybody. But the good thing of RRTs when regarding exploration is that RRTs, which is a sampling-based path planner, they implicitly are very well suited for exploration because they explore the space. There is theoretical results that show how an RRT naturally just explore the space. So they are very good candidates to generate candidate paths. So basically, at the end of the day, for exploring, each robot that I will generate is a set of paths using this RRT. And then we will decide which path to follow so that is the most informative one. The second thing is the information metric we use. And again, this information metric is, we need to use it in order to compare the paths. So we will have some path suggestions given by the RRT, and we have to decide which one is the best one from the point of view of the information we get about the process. And let me explain with this figure, hopefully can be clear. So imagine we have this situation. So this red drone is our robot. And these golden stars is the path we have already carried out. So these are the positions, this X, that we have already measured and are used in the Gaussian process to predict new positions. And now, from the RRT, we can have a set of candidate paths like these two paths. This PI1 and PI2 are two candidate paths for the same drone. And we have to compare them to see which one is better from the point of view of the information gathering. And we have different possibilities. We can, for instance, use the entropy of the path. So we can, with the Gaussian process, predict the uncertainty of these positions for each of the paths. And we can compute the entropy of the joint distribution of these new points. This is one possibility. Another possibility is to use mutual information. The mutual information is, if you remember, the mutual information between two random variables is basically the reduction of entropy on one variable that we will get by observing the other variable. So one idea would be to compute the mutual information between the path and the rest of the environment. For instance, this mutual information we call here non-measure is the mutual information between the path I will perform and the rest of the environment I have not visited yet. The idea is that if we select the path with the maximum of this mutual information, we will get the path that gives more information about the rest of the space, okay? We could be very interesting. So I don't need perhaps to visit every point here, but I will get a lot of information about the rest of the space. There is a variant of this, which called mutual information all, in which the mutual information is between the path and all the space, including the space I have visited before. This may seem, why it's important to consider adequately these options, because we want an information metric that has some interesting, we would like to have these two interesting properties. One is monotonicity. So we want an information metric that takes into account the principle that information never hurts. So if you get more measurements, you will have the same or higher information, but not decreasing, okay? And another important property is to have submodularity, so that you have diminishing returns. So we would like the naturally longer paths, and when you add more information, you get less and less gain. So in somehow you balance longer paths with the information. And actually, you are not careful with that. You can see, it's easy to see, these are just simulations we did, but theoretically you can also see it, that the entropy of a path is non-monotonic and non-submodular. And this is because actually we are talking about differential entropy. We are talking about continuous distributions, and entropy can even be negative. And you can have longer paths that have less entropy. And it's very tricky to compare paths of different lengths by using the entropy. So it's really a bad measurement for this case. Between the mutual information is good because it has this submodularity property, but in particular, it's important to use the second version because the second version is also monotonous, while the mutual information with respect to the parts you have not visited, it doesn't need to be monotonous. Finally, the final component is, okay, we want to take the decisions in a decentralized way, and we want to take into account constraints. So for that, we use a distributed constraint optimization algorithm, and in particular MAVs, that I guess also you may be familiar on it, but it's a method to optimize some decision variables over factor graphs. And they can be applied to multi-robot systems. Let me just put it as a very quick academic example. So imagine that you have these 3 robots, and each robot has to decide a color, okay, blue and red. And basically, the idea is to, in a distributed way, decide the colors so that not a neighbor robot select the same color. So basically, the decisions could be, correct decisions would be these 2. So red, blue, red, or blue, red, blue, okay? One way to approach this problem would be to put a utility function that gives very high values when you have a correct solution and very negative values when you have an incorrect solution, and then optimize it. If this utility function can be decomposed like this in some components in which they only depend on decision variables of a robot and perhaps the neighborhoods, then, well, this could be like the factor graph representation of this function. And MAVs can be applied to this graph. MAVs is a message passing algorithm. So it can, in a distributed way, just by sending messages through these edges, it can obtain the optimal decision variables D1, D3, and D2. And actually, if we have a problem in which we can decompose the utility function in this way, this means that the optimization problem can be solved in a decentralized way between the robots. And actually, this is what we use in our approach. Of course, not for this very simple problem, but I will explain just in the next slides. So this is now we have our final setup of our algorithm, and I will just finish the explanation quickly. So the first idea is that each robot in the fleet, they will generate paths, candidates, using the RRT as I mentioned before. And our decision, basically the output of our decision making should be which path each robot has to follow. And for that, we will use the MAVs. The problem is that if we use a decision variable directly the paths, then we are talking about hundreds of paths, and the computational complexity of MAVs is quite high. So what we do before that is to cluster the paths. So we cluster the paths in spatiotemporal clusters. So the points of the paths that are close in time and space, they are clustered together. So basically, we will reduce the distributed decision to the cluster that is selected by each robot. Whenever a robot selects a cluster, later it will select within the cluster the best path from the point of view of the information metric. The decision for the cluster selection between all the robots is done in a decentralized way using the MAVs. And the utility function we use consists of 2 components, an information gathering component and another component which is related to the constraints. The information gathering is, as I said, is just the mutual information between the clusters and the whole space I want to explore. And it can be seen under very mild assumptions how this can be also computed in a decentralized way. The second component is the constraint satisfaction, that we use it, as I said before, to avoid collisions between the robots, and also to maintain the connectivity within the network. We actually applied this to a real problem. We had a collaboration with the Australian Centre of Field Robotics in Sydney, there in Australia, and we used this setup in order for a fleet of robots to explore thermals. I don't know if you know, but the group of Salah Sukaria, they have been quite interested on soaring. So you have gliders that they can use these thermals, which basically they offer a vertical component of velocity so that you can use the thermals to gain energy and then to keep flying more and more time. And for that, you need to detect and you need to map where the thermals are. So we use our Gaussian process and active exploration algorithm in order to apply to this kind of application, the multi-robot exploration of thermals. We, of course, did first simulations, and in simulation, we used them to see how the algorithm would offer gains in efficiency with respect to the other approaches, and the gains are super linear in the number of robots. It means that the more robots you add, the higher the gain you get. It's not just a linear increase on the gains. And also how we can, with our algorithm, we can attain the constraints in a large percentage of time. Not 100% because we are softening the constraints, but mainly the network connectivity is the one that is more difficult to maintain. But as we are using a decentralized system, even if you have the system with some disconnections, you can still maintain the system working. Also, given the decentralization of the algorithm, it means that this scales much better with the number of robots in the network. You can see here, this graph, it shows the size of the neighborhood for each robot. In a decentralized system, the computation is depending on the size of the neighborhood and not on the size of the whole fleet. If you have a fully connected system and everybody sending information to everybody, then you have a linear increase on the neighborhood, which means an exponential increase in the complexity of the decision making in each robot. And finally, we apply the same thing to real experiments. We fly, in this case, an experiment with three robots in which we wanted to estimate these thermals, and we compare. And you can visit those papers in which we report how the method is able to efficiently map the thermals present in the environment. So, for the sake of the time, I will be just concluding. So. Basically, as a summary of the talk, I will try to deal with the problem of multi-robot separation, which basically is to take the actions that maximize the robot information about the environment. It is important for this kind of systems, and I think tomorrow you will have additional talks on this, to consider non-myopic approaches, so in which planning is involved, and that we are able to handle at the same time inter-robot constraints. And the key for scalability and robustness is decentralization. So if we have systems that depend only in local processing and at most in local communication, then this will lead to systems that are more scalable because as I said, the complexity depends only on the size of the neighborhood and not on the size of the whole fleet, but also they are robust against communications dropouts. And for exploration, is very important to analyze properly the theoretical properties of information metrics, which are key to achieve the objectives. And with this, just talking about work we are doing right now. So we are working on extending this to relax the assumptions. Now we are working on the integrated exploration when we take into account SLAM at the same time. You can have uncertainties on the pose. You can have uncertainties on the obstacles. And we want to do this in an integrated way. And actually, we are following multi-objective optimization approaches because this is by definition a multi-objective problem. And we want to also explore this kind of approaches and also deal with dynamic processes and not all processes that are time invariant. And of course, as seems that everybody else, we are also having a look to learning-based approaches instead of model-based approaches. And that's all. With this, I'm finished my talk and I open to questions. Just with this slide in which a set of agents are exploring the slide itself using one of these algorithms.
Okay, Professor Merino, thank you very much. I want to ask what's your view about deep reinforcement learning? Like recently, many works have attempted to apply deep reinforcement learning for multi-robot cooperation. What's your view about their advantages and disadvantages? And do you think it is really possible to apply deep reinforcement learning into real-world applications?
Yeah, in fact, so the answer is that yes, you can apply it. Actually, my former PhD, Alberto, now in his postdoc, he was doing some deep reinforcement learning applied to information gathering. So the answer is yes. I think that's I think right now the best is a combination of things. So you can use, for instance, deep learning in general, so that you can learn models that helps you to estimate the information gain of future paths. This can be used, for instance, to have like more powerful models in order to predict how well or how good the information of your plans will be in the future. And there are many groups that are trying these kind of things with different models, even with reinforcement learning and also with deep learning using attention and things like this. So the answer is, I think, yes, this will be a tool that can be helpful, in particular right now in combination with the classical planning approaches as well.
Okay. But I think deep reinforcement learning is very like fragile to the auto distribution data. If you change I think deep reinforcement learning is very sensitive to the auto distribution data. Right?
Yeah.
So if you change the environment, then the model will fail. So
yeah, I completely agree. I mean, so what I think is, I mean, we know a lot of things. So let's combine the best of both worlds, right? So if we combine the things we know from the theoretical point of view on this kind of application, and then we can use powerful models, but at the same time avoid this kind of situation as you mentioned. You have auto distribution data, and then you can very weird decisions and so on. So we can combine the best of both worlds. I think that we will have much more powerful algorithms there.
Okay. There are some questions from the audience. There's a question from Xi Yueguo. He asked, how does the system handle uncertainties, such as dynamic environment, occlusions, and noise? So, yeah, let me just stop sharing here if I can. Yeah. Okay, just a moment. Yeah. So, a good question. So in this particular, so in the last part of the presentation, what we are doing is actually reducing the uncertainty. So the objective of so we model the uncertainties with the Gaussian process, and we directly try to reduce them. And we are, in that particular work, we are still not handling dynamic scenarios because we are using just a spatially distributed Gaussian process. You could, in theory, apply the same ideas to a spatiotemporal Gaussian process. But then, of course, there is an important additional complexity because your plans, so you now have to do motion planning. So you need to take the time into account in your plans as well. But I mean, there are approaches like this, and in theory, many of the ideas can be also applied to the same problem. In some of the works we have done related to this, but not directly to the exploration part, we have used this in order to handle uncertainties is to use these partially observable Markov decision processes. And we have some papers on this. PondDPs. The problem with PondDPs is that they are very computationally demanding. They don't scale well. So we try to, again, using decentralization, because in particular, if you apply to a multi-robot system in which the action space basically scales exponentially with the number of robots, then you have to resort to this kind of decentralization in order to get algorithms that can cope with the complexity in this case. Okay. There is also another question from Hao Boluo. He said, "Thank you for your nice talk." His question is how to plan paths distributedly when there are position constraints between different robots. For example, a distance of 1 meter needs to be maintained between every 2 drones.
Yeah. So so you mean about how to handle the constraints, right?
Yes.
So yeah. So the thing is that actually this is what we do with this MAVs algorithm. So the drones that are neighbors, they exchange their decision spaces. They basically exchange, in the talk I mentioned, these clusters of paths. So they exchange that only with the neighbors, okay? So the decisions are taking into account the cluster that the other drone can take, and using the constraints are encoded into the utility function. So we have this penalty, very high penalty whenever you have paths that go very close to them, and low penalty if they are far away. So this is directly handled by the MAVs and by the sharing of the decision spaces of neighbor robots, okay?
Okay, there's another question. The audience asked, can Professor give some advice on how to choose proper information metrics?
Well, the thing is that it just properly understand the theoretical characteristics of the metric and your problem. If the model you're using continuous or discrete distributions, and properly know what are the properties here. As I said, entropy is the typical way to go, but sometimes, as I said, for instance, in this case, for computing the information content of a path, it can be tricky and it could lead to incorrect decisions. Okay, so the answer is, please analyze well the theoretical properties of each metric. Also performing experiments can give you some inputs of how the things are behaving there. Okay, and we know, I mean, this is well established, so we know the typical metrics we can use. But it's important to for each problem to see what is the best one to be applied. Okay.
Okay. Okay, Professor Merino, there are no more questions. Thank you very much.
Okay, thank you.
Yeah, we are hoping to invite you again in the future to give our.
I will be.
Yeah, to give us.
Will be more than glad.
Talk. Yes. Thank you very much.
Thank you very much. And if anybody wants that, you know, you can contact me. You have the details also in the slides and so on. Okay.
Okay.
Thank you, everybody.
Yeah. Thank you very much.
Thank you. Thank you. Bye.
Thank you everyone for your attention to our AIRS in the Air event. We will have Prof. Sebastian Heron from the CMU and Prof. Junjie Hu from the Tokyo University on May 18. Thursday, please don't miss that.